Okay, hello. Okay, good night everybody. Yeah. Welcome. Good night, world. I'm ATM4131 and welcome to my stream. And today, let's continue where we left off. Well, last week, or last 2 weeks. It's last 2 weeks because last week I'm playing ETS2 for a week non-stop. Well, you can say non-stop. No, more like I am only playing ETS2. So let's go. Let's continue where we left off. Okay, now we got to the chapter 2 of the introduction of the quantum mechanics, the time-independent Schrödinger equation. Okay. Okay, probably let me read you to sleep. This is just take this as a bedtime stories, but it's about a cat. About a cat in a box. So yeah, let's we start 2.1 stationary states. Okay. In chapter 1 we talk a lot about the wave function and how you use it to calculate various quantities of interest. The time has come to stop procrastinating and confront what is logically the prior question. How do you get CXT in the first place? How do you go about solving the Schrödinger equation? I shall assume for all of this capture and most of this book that the potential V is independent. Is independent of T. In that case, the Schrödinger equation can be solved by the method of separation of variables. The physicist's first line of attack on any partial differential equation. Okay. We look for solutions that are simple products. Okay, CXT equals CXFT. Where C oh, C dalam kurung lowercase. Chaos Infora. Oh, hello Chaos, welcome to my stream. Oh yes, I don't understand a thing. Well, don't worry, me too. Because there's a saying, if you say you understand quantum mechanics, then you don't understand quantum mechanics. So let's see, where am I? Oh, okay, where C lowercase is a function of x alone and f is a function of t alone. Oh, so this is the separation of the variable between the x, the function of x, and the function of t. The x is like the distance probably, the distance, and t is, well, time. T is, yeah, well, it's time. On its face, this is an absolute restriction, and we cannot hope to get more than a tiny subset of all solutions in this way. But hang on, because the solutions we do obtain turn out to be of great interest. Moreover, as is typically the case with separation of variables, we will be able at the end to patch together the separable solutions in such a way as to construct the most general solutions. Oh. This. Oh, man, the footnotes. It is tiresome to keep saying potential energy function. So, most people just call V the potential, even though this invites occasional confusion with electric potential, which is actually potential energy per unit charge. Okay, for separable solutions, we have equation. I don't bother to say it. Ordinary derivatives now, and the Schrödinger equation. It's, yeah, like this thing. Yeah, the Greek letters, or dividing through by CF, another Greek letter. Now on the left side is a function of t alone, and the right side is a function of x alone. Oh, is that? Oh yeah. The only way this can possibly be true is if both sides are in fact constant. Otherwise, by varying t, I could change the left side without touching the right side. Both sides are constant. Oh, yeah. Oh, I could change the left side without touching the right side, and the two would no longer be equal. That's a subtle but crucial argument, so if it's new to you, be sure to pause and think it through. Okay, I will pause for a little bit. Okay, so assume that the t pairing t change the left. Oh, yeah, I get what you mean. For reasons that will appear in a moment, we shall call the separation constant E, then, oh, so the right hand side of the equation is, assume that's, oh, no, it's actually the left side, assume that is E, the separation constant, or, yeah, the F dt equals, yeah, this is basically structuring the equation, and something, we got this. Or blah 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 blah. Oh yeah, the fifth C equals the if C. Separation of variables has turned a partial differential equation into two ordinary differential equations. Equations 2.3 and 2.4. The first of this is easy to solve, just multiply through by dt and integrate. The general solution is c exponent blah 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 blah. But we might as well absorb the constant c into c. Since the quantity of the interest is the product cf, then ft equals exponent minus I blah 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 blah. The second, equation 2.4, is called the time-independent Schrödinger equation. We can go no further with it until the potential Vx is specified. Oh yeah? Oh yes, it is. Yeah, because the time-dependent part is assumed to be constant. It is named the time-independent Schrödinger equation. So in order to solve this, yeah, we need to know the Vx. The rest of this chapter will be devoted to solving the time-independent Schrödinger equation for a variety of simple potentials. But before we get to that, I would like to consider further the question, what's so great about separable solutions? After all, most solutions to the time-dependent Schrödinger equation do not take form Cx ft. I offer the answers, two of them physical and one mathematical. 1. They are stationary states, although the wave function itself, yeah, it's like this, does obviously depend on t, the probability density, some long as equation does not. The time dependence cancels out. The same thing happens in calculating the expectation value of any dynamical variable. Equation 1.36 reduces to some equation. Every expectation value is constant in time. We might as well drop the factor ft altogether and simply use c in the place of and simply use the lowercase c in the place of uppercase c. Indeed, it is common to refer to lowercase c as the wave function, but this is lovely language that can be dangerous. And it is important to remember that the true wave function always carries that exponential time-dependent factor. In particular, x is constant, and hence, equation 1.33, the p inside the what do we call the dalam kurung in English, I don't know, the kurung siku, the funky p equals 0. Nothing ever happens in a stationary state. Oh, so in a stationary state, the answer is 0 because nothing ever happens. 2. They are states of the definite total energy. In classical mechanics, the total energy, the kinetic plus potential, is called the Hamiltonian. Hxp equals, yeah, the other equations. Oh, Oh, there's Vx here. Okay. The corresponding Hamiltonian operator obtained by the canonical substitution P to the blah 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 is therefore H equals this equation. Thus, the time-independent Schrödinger equation 2.4, can be written Hc equals Efc. Whoa! Oh yeah. Oh yeah, the Hc equals the Efc. For normalizable solutions, E must be real. Oh, the footnote. Oh, where is the footnote 3? Where? Oh, where is the footnote 3? Oh, the time dependence cancels out. Okay, whenever confusions might arise, I'll put a hat on the operator to distinguish it from the dynamical variable it represents. Well, I don't, I have no idea what is the dynamical variable or something. Okay, and the expectation value of the total energy is H equals equation. Note that the normalization of the psi entails the normalization of the lowercase psi. Moreover, this equation, and hence another equation. Oh, so the h square is equal to e square. So the standard deviation in h is given by 0. Okay, but remember, if delta equals 0, this is not delta, this is sigma. But remember, if sigma equals 0, then every member of the sample must share the same value. The distribution has 0 spread. Yeah, another insight on statistics: the standard deviation it represents on how spread your data is. The higher the standard deviation, the more diverse your data will be. So if you have the really high standard deviations, it can be range from as small as 1 to as big as 1 million. It will have a really big standard deviation. So that's an insight on statistics. But yeah, this needs a slide. What do you call it? A slide understanding on statistics. Since it has the standard deviation and such. Conclusion: a separable solution has the property that every measurement of the total energy is certain to return the value E. That's why I chose that letter for the separation constant. 3. The general solution is a linear combination of separable solutions. As we are about to discover, the time-independent Schrödinger equation, like the previous equation in the 2.4, yields an infinite collection of solutions, like the C1x, C2x, C3x, and such, and so on, each with its associated value of the separation constant, E1, E2, E3, and so on. Thus, there is a difference wave function for each allowed energy. Yeah, these equations, but this time it has 1, 2, 3, and such. Now, as you can easily check for yourself, the time-dependent Schrödinger equation, like the equation 1.1. Oh, wait, it's too it's too long to scroll up. So let's just go on. Oh, where am I? Where am I? Oh. Thus, what is has the property of any linear combination of solution is itself a solution. Once we have found the separable solutions, then we can immediately construct a much more general solution of the form. Equation 2.14. It so happens that every solution to the time-dependent Schrödinger equation can be written in this form. It is simply a matter of finding the right constants, so as to fit the initial conditions for the problem at hand. You will see in the following sections how all this works out in practice, and in Chapter 3 we will put it into more elegant language. But the main point is, once you have solved the time-independent Schrödinger equation, you are essentially done. Getting from there to the general solution of the time-dependent Schrödinger equation is simple and straightforward. Oh, okay. So I'm not gonna do the problem. Okay, to point to the infinite square well. Wait, I'm gonna check. I'm gonna check how many sub capture does this have? Oh, wait, we are on the harmonic oscillator. Free particle. The finite square well. Oh. Okay, this is a long capture. This is a long capture. 88 from the 88 to the wait, where's the infinite square well, yeah, it kind of took 30 pages to finish the capture too. Wait, where's the infinite square well? Where is this? Oh no, this is the harmonic oscillator. Oh, it's 40 each page to finish the capture. Probably I will split it into two two sessions to finish the capture too. Okay, the infinite square well. Suppose that the Vx is 0 if 0 is in the range within. If x is in the range between 0 and a, and infinite if otherwise. So it's like just the figure 2.1. It's like this, yeah, in between the range of 0 to a, it's 0, but on the other locations it's infinite. A particle in this potential is completely free except at the two ends x0 and x equals a, where an infinite force prevents it from escaping. A classical model would be a car on a frictionless horizontal air track. With perfectly elastic bumpers, it just keeps bouncing back and forth forever. Oh, with frequently. Outside the well, psi x equals 0, the probability of finding the particle that is 0 inside the well, where phi equals 0, are time-independent Schrödinger equation. Equation 2.4 reads the equation or another equation where another equation. By writing it in this way, I have tacitly assumed that E is greater than 0. Is greater or equals 0. We know from problem 2.2 that E is less than 0 doesn't work. Yeah, I can see why E less than 0 doesn't work, because it's the K wouldn't be real. Okay, equation 2.17 is the classical simple harmonic oscillator equation. The general solution is yes, the sin and cos. Where a and b are arbitrary constants. Typically, these constants are fixed by the boundary conditions of the problem. What are the appropriate boundary conditions for psi x? Ordinarily, both psi and psi differential turunan psi terhadap x are continuous, but where the potential goes to infinity, only the first of these applies. I'll prove these boundary conditions and account for the exception when phi equals infinity later on. For now, I hope you will trust me. Yeah. Yeah, I don't know anything, so I decide to trust you. Continuity of psi x requires that psi 0 equals psi a equals 0. So, as to join in onto the solution outside the well, what does this tell us about a and b? Well, well, psi 0 equals a sin 0 plus b cos 0 equals b. Oh, it's b equals 0, and hence psi x equals a sin kx. Then psi a equals a sin ka. So either a equals 0, in which case we left with the trivial normalized solution psi x equals 0, or else sin ka equals 0, which means that ka equals to 0, p to p, 3p, and so on. But k is equals 0 is no good. Again, that will imply psi x equals 0. And the negative solutions give nothing new, since sin minus theta equals minus sin theta. And we can absorb the minus sign into the a, so the distinct solutions are kn equals np per a with n equals to 1, 2, 3, and so on. Curiously, the boundary condition at x equals a does not determine the constant a, but rather the constant k, and hence the possible values of e. Just like the equation. Like the equation. In sharp contrast to the classical case, a quantum particle in the infinite square well cannot have just any old energy, only these special allowed values. Well, how do we fix the constant a? Answer, we normalize c. Also, the normalization of c. Oh, so this is the c, and yeah, just square it, and we got 1. So from the normalization we got this, and we can find the a. This only determines the magnitude of a, but it is seamless to take the positive real root. A equals to square root 2 per a. The phase of a carries no physical significance anyways. Set the well, then the solutions are this. As promised, the time-independent Schrödinger equation has therefore an infinite set of solutions, one for its integral n. The first few of these are plotted in figure 2.2. They look just like standing waves on a string of length a. Psi 1, which carries the lowest energy, is called the ground state. The others, whose energies increase in proportion of n squared, are called excited states. As a group, the functions psi and x have something interesting and important properties. One, they are alternatively even and odd with respect to the center of the well. Psi 1 is even, psi 2 is odd, and so on. As you go up by energy, its successive state has one more node, or zero crossing. Psi 1 has none, the endpoints doesn't count. Psi 2 has 2, psi 3 has psi 2 has 2, 1, psi 3 has 2, and so on. Okay, let's just skip the footnote. Oh, so this is the first three stationary states of the infinite square well. Yeah, so this is the wave like this, and like this, and like this. 3, they are mutually orthogonal in the sense that this equation whenever m does not equal to n. Proof? The proof is like this. Note that this argument doesn't work if m equals n. Can you spot the point at which it fails? Oh, okay. Yeah, spot it already. It's in here. Well, m minus n is equal 0, and for 0 it's basically divided by 0 is basically it's not only it will break the law of the government, the country, it will also break the laws of mathematics, the physics. In that case, normalization tells us that the integral is 1. In fact, we can combine orthogonality and normalization into a single statement like this. where delta Mn, the so-called Kronecker delta, is defined in the usual way like this. We say that the size are orthonormal, for they are complete, in the sense that any other function fx can be expressed as a linear combination of them. Another equation, and I'm not about to prove the completeness of this function, but if you studied advanced calculus, you will recognize that 2.28 is nothing but the Fourier series of fx. And that the fact that any function can be expanded in this way is sometimes called the Dirichlet Theorem. The expansion coefficient beautifully exploits the orthonormality of psi n. Multiply both sides of the equation by psi m x star and integrate that like this. Notice how Kronecker delta kills every term in the sum except the one for which n equals m. Yeah. Thus, the mth coefficient in the expansion of fx is given by another equation. Its four properties are extremely powerful, and they are not peculiar to the infinite square well. The first is true whenever the potential itself is an even function. The second is universal, regardless of the shape of the potential. Orthogonality is also quite general. I will show you the proof in chapter 3. Completeness holds all the potentials you are likely to encounter. But the proofs tend to be nasty and laborious. I'm afraid most physicists simply assume completeness and hope for the best. The stationary states, equation 2.6, for the infinite square well are evidently like this. I claim that the most general solutions to the time-dependent equation, Schrödinger equation, is a linear combination of stationary states, like the equation 2.32. If you doubt that this is a solution, by all means check it. It remains only for me to demonstrate that I can fit any prescribed initial wave function x0 by appropriate choice of the coefficient Cn. According to the equation 2.22, this equation, the completeness of the C confirmed in this case by the Dirichlet Theorem, guarantees that I can always express capital C x0 in this way, and their orthonormality licensed the use of Fourier streak to determine the actual coefficients. That does it. Given the initial wave function uppercase psi 0, the x0, we first complete the expansion coefficient Cn. Using equation 2.33, and then plug this into equation 2.32 to obtain psi capital Xt. Armed with the wave function, we are in a position to compute any dynamical quantities of interest using the procedures in chapter 1. And the same ritual applies to any potential. The only thing that changes are the functional form of the size and the equation for the allowed energies. Okay, so I'm just gonna skip the problem. Oh, we got into the harmonic oscillator. Wait, let me take a break. Man, this kind of exhausting. reading books like this kind of exhausting. Okay. Okay, guys. If you haven't hydrated yet, stay hydrated. If you haven't stretched yet, go get stretched. Stretch your body. Urgh. I'm just an ATM machine, of course I can't stretch my body. But yeah, the equivalent thing of stretching is, well, refreshing. Well, refresh, just like the PC refresh, like you press the F5 to refresh the system. Well, I'm I'm refreshing, but literally using the refresh function for the computers. Nah. Okay. Shall we continue then? Okay, 2.3, the harmonic oscillator. The paradigm. How do I spell paradigm? Paradigm. For a classical harmonic oscillator is a mass M attached to a spring of force constant K. The motion is governed by Hooke's law. Oh yeah, this is the spring of equation, the Hooke's law. F equals minus kx equals to m to the double the turunan pangkat 2 dari x terhadap t. How do I say that in English? I don't know. As always, we ignore friction. And the solution is xt equals to a sin the omega t plus b cos omega t, where omega is the angular frequency of oscillation. The potential energy is like this. Its graph is a parabola. Okay. Of course, there's no such thing as a perfect simple harmonic oscillator. If you stretch it too far, the spring is going to break, and typically Hooke's law fails long before the point is reached. But practically any potential is approximately parabolic. In the neighborhood of a local minimum, like in the figure 2.3. Oh, where is the figure 2.3? Oh, okay. I, I don't know the reference. Aku nggak tahu referensinya. Formally, if we expand the Vx in a Taylor series about the minimum, yeah, the Vx equals Vx0 plus V tanda kutip x0 blah 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 blah. Subtract Vx0, you can add the constant to Vx with impunity since that doesn't change the force. Recognize that V derivative x0 equals 0. Since x0 is a minimum, and drop the higher order terms, which are negligible as long as x minus x0 stays small. The potential becomes, if Vx is approximately equal to 1. Equation. Which describes the simple harmonic oscillation about the point x0 with an effective spin constant k equals blah blah blah. That's why the simple harmonic oscillator is so important. Virtually any oscillatory motion is approximately simple harmonic, as long as the amplitude is small. Okay, the quantum problem though is to solve the Schrödinger equation for the potential. Just like this. Okay, it is customary to eliminate the spring constant in favor of the classical frequency using the equation 2.36. As we have seen, it suffices to solve the time-independent Schrödinger equation 2.39. In the literature, you will find two entirely different approaches to this problem. The first is a straightforward brute force solution to the differential equation using the method of power series expansion. It has the virtue that the same strategy can be applied to many other potentials. In fact, we will use it in Capture 4 to treat the column's potential. The second is a diabolically clever algebraic technique using the so-called ladder operation. Ladder operation. Oh, that's the one that is used in the, what do you call it? The Jordan. Oh, hello Atma. Hello Jordan. Welcome to my stream. Oh, wait. I have mistaken from ladder operator to to the ladder logic. Oh, I have mistaken between ladder operators and ladder logic. Yeah, it's a different story. Ladder logic is a different story. It's the kind of programming language that you use to program PLCs. Yeah. Yeah, at this point you can tell that I am overheating again. I'm getting sleepy again. Yeah, later operators. No, no, no. It's not about the PLC. Not about the industrial. Not about the industrial things. The industrial machineries. No, it's a different thing. Yeah, later operator. I'll show you the algebraic method first, because it is quicker and simpler and more fun. If you want to skip the analytic method for now, that's fine, but you should certainly plan to study it at some stage. Okay, let's go. Okay, the algebraic method. To begin with, let's write like this. And then, the idea is to factor the term in square brackets. If these were numbers, it will be easy. So it's the expansion. It is expanded like this. Okay. Assume this is a quadratic. What do you call it? The quadratic complex equation. Here, however, is not quite simple, because U and V are operators, and operators do not in general commute. UV is not the same as VU. This does invite us to take a look at the expressions. A plus minus equals to 1, blah 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 blah. Oh yeah, so this is the, what is their product? A minus A plus. Warning, operators can be slippery to work with in the abstract, and you are bound to make mistakes unless you give them a test function fx to act on. At the end, you can throw away the test function, and you will be left with an equation involving the operators alone. In the present case, we have a minus a plus fx. Just like this, like this, like this. I don't want to even bother to read the blah 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 blah. Okay, I use this in the last step. Discarding the test function, we conclude that a minus a plus equals this. Evidently, the equation 2.4t does not factor perfectly. That's an extra term. This? Yeah, this. However, if we pull this over to the other side, the Schrödinger equation becomes like this. Notice that the ordering of the factors a plus and a min is important here. The same argument with a plus on the left yields this. Oh, wait. Okay, spot the difference game. Oh yeah, the half, the 1 per 2 h with the function bar omega. If the a minus a plus it's plus, the a plus a minus it's minus. Thus the a plus a minus a plus subtract by a plus a minus is h function bar omega. And the Schrödinger equation can also be written like this. Like this. Now, here comes the crucial step. I claim that if C satisfies the Schrödinger equation with the energy E, then A plus C satisfies the Schrödinger equation with energy E. Proof? Yeah, I'm not gonna read the whole proving. Notice that well as the ordering of a plus and a minus does matter, the ordering of a plus minus and any constants such as this does not. By the same token, a minus c is a solution with the energy this. However, here then is a wonderful machine for grinding out new solutions. With the higher and lower energies, if we can just find one solution to get started, we call a plus minus ladder operators. So the a plus minus is the ladder operator. Because they allow us to climb and up and down in the energy, a plus is called the raising operator and the a minus is the lowering operator. The ladder of the states is illustrated in the figure 2.4. Wait, let me see. This is the figure 2.4. So this is the ladder operator. To raise, you just just multiply it by a plus. If you want to lower it, just multiply it with A minus. I almost say A minor. Okay, well. Then what? But wait, what if I apply the lowering operator repeatedly? Eventually, I'm going to reach the state with energy less than 0, which, according to the general theorem in problem 2.2, does not exist. At some point, the machine must fail. How can that happen? We know that A minus C is a new solution to the Schrödinger equation, but there is no guarantee that it will be normalizable. It might be 0, it might, or its square. Integral might be infinite. Problem 2.11 rules out the latter possibility. Conclusion: there must occur a loss rank, let's call it psi 0, such as this. That is to say that, or this differential equation of psi 0 is easy to solve. This to this. Now we are playing with the learn. Psi 0 equals blah 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 plus constant. So this, to determine the energy of this state, we plug it into the Schrödinger equation in the form of equation 2.46. A plus A minus plus I minus plus blah 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 equals to blah blah blah, and explain the fact that A minus V0 equals 0. Evidently, E0 equals to 1 per 2 H omega. With our foot now securely planted on the bottom rung, the ground state of the quantum oscillator, we simply apply the racing operator to generate the excited states. So like this. The method does not immediately determine the normalization factor AN. I will let you work that out for yourself in problem 2.12. For example, this which simplifies to that. I wouldn't want to calculate. I wouldn't want to calculate the psi 50 in this way, but never mind. We have found all the allowed energies, and in principle we have determined the stationary states. The rest is just computation. Okay. So yeah, the 2.3.0, the analytic method. The before is just the algebraic method. Okay. So now for the analytic method, we return now to the Schrödinger equation for the harmonic oscillator. Equation 2.39, like this. Things look a little clearer if we introduce the dimensionless variable. Oh no! Oh no! Oh no! Look at this! Look at this! Look at this! This variable, this man. Yeah, this variable, this is very tough to write. If you try to handwrite this variable, you will end up just like a random squiggle. Just a random squiggle that or tornado. Man, this is like the, well, screw this variable. Even in MIT conventions, there is some there's one MIT student that rants about this variable. Oh no, the student rants about the zeta variables instead of the. This is the key C. It is written xi c, but it's probably pronounced as key. Wait, no. Pokoknya C aja, C. I don't know how to pronounce, so I will pronounce it the opinion way. The C is C. Yeah, the C variable. Things look like a little cleaner if we introduce the dimensionless variable C. In terms of C, the Schrödinger equation reads like this. Yeah, the C squared minus K, blah blah blah. Where the K is the energy in units of half H omega. This, Planck omega. The H with the funky bar is Planck. I just remember it's the Planck constant. Or is it? Our problem is to solve equation 2.56 and in the process obtain the allowed values of k and hence with e. To begin with, note that at very large c, which is to say at very large x, c squared completely dominates over the constant k. So in this regime, this equation, which has the approximate solution, check it. Oh man, it's getting harder and harder to read the equations. So it has the approximate solutions like the equation 2.59. The b term is clearly not normalizable. It blows up as x to infinity, limit to infinity. The physically acceptable solutions then have the asymptotic form of this. This suggests that we peel off the exponential part. This in hopes that what remains, hc, has a simpler functional form than psi c itself. Differentiating equation 2.61, we have this and that. So the Schrödinger equation becomes like this. I propose to look for a solution to equation 2.62 in the form of a power series in C like this. Yeah, the Taylor series. Hc equals to a0 plus a1c plus a2c squared and so on. Differentiating the series term by term, this and like this, putting this into equation 2.62, we found this. It follows from the uniqueness of power series expansions that the coefficients of each power of c must vanish like this, and hence that this recursion formula is entirely equivalent to the Schrödinger equation itself. Given a0, it enables us in principle to generate a2, a4, a6 and so on, and given a1, it generates a3, a5, a7. Let us apply it. Hc equals to h even c plus h odd c, where h even c equals to a0 plus blah 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 is an even function of c, since it involves only even powers built on a0, and h odd c equals to this is an odd function built on a1. Thus, equation 2.65 determines hc in terms of two arbitrary constants a0 and a1, which is just what we would expect for a second-order differential equation. However, not all the solutions so obtained are normalizable. For at very large j, the recursion formula becomes approximately like this: aj plus 2 approximately to j aj. With the approximate solution, this for some constant c, and this yields at large c, where the higher powers dominate like this. Now, if h goes like exponent c squared, then psi, remember the lowercase psi, that's what we are trying to calculate. Oh, thanks for the reminder, Griffiths. It goes like exponent c squared per 2, which is precisely the asymptotic behavior we don't want. There is only one way to wiggle out of this. For normalizable solutions, the power series must terminate. There must occur some highest j, call it n, such that the recursion formula spits out a n plus 2 equals 0. This will truncate either the series h even or the series h out. The other one must be 0 from the start. For physically acceptable solutions, then we must have k equals to n plus 1. For some positive integer n, which is to say, referring to equation 2.57, that the energy must be on the form of this equation. Thus, we recover by a completely different method the fundamental quantization condition we found algebraically in equation 2.50. For the allowed values of k, the recursion formula reads this: if n equals 0, there is only one term in series. We must pick a1 equals 0 to kill h out, and j equals 0 in the equation 2.68. yields h2 equals 0, h0 c equals to h0, and hence this, which reproduce the equation 2.48 for n equals 1. We pick h0 equals 0, and equation 2.68, which j equals 1 yields h3 equals 0. So h1c equals to a1c, and hence this, confirming the equation 2.51. For n equals 2, j equals 0 yields this and gives a4 equals 0. So this equation and that equation, and so on. Compare problem 2.13, where the same result was obtained by algebraic means. In general, h and c will be a polynomial of degree n in c involving even powers only if n is an even integer and odd powers only if n is an odd integer. Apart from the overall factor a0 or a1, they are the so-called Hermit polynomials, like this, h and c. The first few of them are listed in table 2.1. By tradition, the arbitrarily multiplicative factor is chosen so that the coefficient of the highest power of c is to the power of n. With this convention, the normalized stationary states for the harmonic oscillators are this. Oh, this looks like we are closer to the wave function. They are identical, of course, to the ones we obtained algebraically in equation 2.50 in figure 2.5a. Where I am? Oh, I have plotted c and x for the first few n's. The quantum oscillator is strikingly different from its classical counterpart. Not only are the energies quantized, but the position distributions have some bizarre features. For instance, the probability of finding the particle outside the classically allowed range, that is, with x greater than the classical amplitude for the energy in question, is not 0. See problem 2.50. And in all odd states, the probability of table. Oh, so this is the table, the first few Hermit polynomials. Oh, it's Hermit, not Hermit. Oh, I misread this as Hermit. Well, in truth, it's Hermit. The probability of... Oh my god, this is all graphs. This is all graphs. Finding the particle at the center of the potential well is 0, only at relatively large. And we begin to see some resemblance to the classical case. In figure 2.5b, I have superimposed the classical position distribution on the quantum one for n equals 100. If you smooth out the bumps in the later, the two will fit very well. However, in the classical case, we are talking about the distribution of positions over time for one oscillator, whereas in the quantum case, we are talking about the distribution over an ensemble of identically paired systems. Yeah. Okay, we have arrived to the free particle. Okay, let's break for a bit. Yes, hey. Okay. Napas dulu. Let me breathe. Let me breathe. Okay. Yang mau ke toilet, if you guys want to go to toilet, just go. We will have a 5 minutes break. 5 minutes break. Anyways, I'm also gonna AFK for a little bit. Okay, I'll be back soon. I'm back. Ah, okay. Okay, to point for the free particle, let's continue where we left. We turn next to what should we have been the simplest case of all, the free particle. The free particle. As you will see in a moment, the free particle is in fact a surprisingly subtle and tricky example. The time-independent Schrödinger equation reads this or this. So far, it's the same as inside the infinite square well. The equation 2.0, I don't even bother to scroll up there, so let's just go with it. I'm not gonna scroll up just to find this equation. So let's just go on where the potential is also 0 this time. However, I prefer to write the general solution in exponential form instead of sines and cosines for reasons that will appear in the course. This equation, oh, this form. I swear I have seen this form of equation before. But I forgot the name. It's I forgot the name. Oh yeah, it's just a sines and cosine equation, but in form of exponential. Oh yeah, I get it. Unlike the infinite square well, there are no boundary conditions to restrict the possible values of k and hence of e. The free particle can carry any positive energy, taking on the standard time dependence exponent equation. Pagi, hello Desta Heitman, welcome to my stream. Well, is this morning yet? No, it's still 12. It's still 12 a.m. As we continue. This. And then we finally get this equation. Okay, if any of you guys doesn't understand quantum mechanics, don't worry. I also don't understand quantum mechanics. This is just a book reading stream, not a teaching stream. So I'll just read it for you guys. You can take it as a bedtime story because yeah, it's night already. But yeah, don't worry. That's a saying. If you understand quantum mechanics, if you think you understand quantum mechanics, then you don't understand quantum mechanics. So it's okay. Now, any function of x and t that depends of these variables in the spatial combination x plus minus vt for some constant v represents a wave of fixed profile traveling in the minus plus x direction. Oh well, this looks like, I almost treat it as gun because yeah, that's a Chinese letter exactly look like this, and it reads gun. As beta v, a fixed point on the waveform, for example, a maximum or a minimum corresponds to a fixed value of the argument, and hence to x and t such that x plus minus vt equals constant, or x equals minus plus vt plus constant, which is the formula for the motion in the minus plus acceleration with the constant speed v. Oh wait, actually the plus minus looks like t. I know there's a Chinese letter looks exactly like that, but I forgot how it spells. I forgot how it spells the t. Oh no, it's two. Oh, it's actually pronounced two. Yeah, two. And the minus plus can. Okay, screw this. I'm not gonna I'm not gonna say it as plus minus or minus plus anymore. I will say 2 or can. Oh, so where am I? Which is the formula for the motion in the can x direction with the constant speed v. Since every point on the waveform is moving along with the same velocity, its shape doesn't change as it propagates. Thus, the first term in equation 2.77 represents a wave traveling to the right, and the second term represents a wave of the same energy going to the left. By the way, since they only differ by the sign in front of k, we might as well write this and let k run negative to cover the case of waves traveling to the left. So this is the equation. The speed of these waves is the coefficient of t over the coefficient of x is like this. On the other hand, the classical speed of a free particle with energy E is given by E equals the classic kinetic energy equation, the E equals 1 per 2 mv squared. Pure kinetic since V equals 0. So V classical equals to square root 2E per m equals to 2V quantum. Evidently, a quantum mechanical wave function travels at half the speed of the particle it is supposed to represent. We will return to this paradox in a moment. There is even a more serious problem we need to confront first. This wave function is not normalizable. For this wave function, in the case of a free particle, then the separable solutions do not represent physically realizable states. A free particle cannot exist in a stationary state, or to put it another way, there is no such thing as a free particle with a definite energy. But that doesn't mean the separable solutions are no use to us, for they play a mathematical role that is entirely independent of their physical interpretation. The general solution to the time-dependent Schrödinger equation is still a linear combination of separable solutions. Only this time it's an integral over the continuous variable k instead of a sum over the discrete index n. This, the quantity 1 per square root of 2 pi, is factored out for convenience. What plays the role of the coefficient Cn in equation 2.14 is the combination of these. Now this wave function can be normalizable for appropriate Vk, but it necessarily carries a range of k's and hence the range of energies and speed. We call it a wave packet. In the generic quantum problem, we are given capital psi x0, and we are to find the capital psi xt. For a free particle, the solution has the form of equation 2.83. The only remaining question is how to determine Vk so as to fit the initial wave function. This is the equation. This is a classic problem in Fourier analysis. The answer is provided by Dirichlet Theorem. This is the theorem, and no, I'm not gonna scroll up for the problem. Fk is called the Fourier transform of fx. Oh yeah, the Fourier transform. Yeah, I just realized we have got into the Fourier transform. So the Fourier transform is like that equation, that transformation of equation that transfers from the domain of time into the domain of frequency. Fx is the inverse Fourier transform of fk. The only difference is in the sign of the exponent. There is, of course, some restrictions on the allowable functions. The integral have to exist. For all purposes, this is guaranteed by the physical requirements that the capital C x0 itself be normalized. So, the solution to the generic quantum problem for the free particle is equation 2.83. With this equation, I'd love to work out an example for you, starting with a specific function c x0, for which we could actually calculate Vk. and then doing the integral integration to point at t to obtain the capital C xt in a closed form. Unfortunately, manageable cases are hard to come by, and I want to save the best example for you to work out yourself. No thanks. Be sure, therefore, to study problem 2.22 with particular care. I return now the paradox noted earlier, the fact that the separable solution Vkxt travels at the wrong speed for the particle it ostensibly represents. Strictly speaking, the problem evaporated when we discovered that the Ck is not a physically achievable state. Nevertheless, it is of interest to discover how information about a particle velocity is carried by the wave function. The essential idea is this: a wave packet is a sinusoidal function whose amplitude is modulated by v. It consists of ripples contained within an envelope. What corresponds to the particle velocity is not the speed of the individual ripples, the so-called phase velocity, but rather the speed of the envelope, the group velocity. Oh yeah, I get it. Which, depending on the nature of the waves, can be greater than, less than, or equal to the velocity of the ripples that go to make it up. For waves on a string, the group velocity is the same as the phase velocity. For water waves, it is 1/2 the phase velocity. You may have noticed when you toss a rock in a pond, if you concentrate on a particular ripple, you will see it build up from the rear, move forward through the group, and fade away on the front, while the group as a whole propagates out of the half the speed. What I need to show is that for the wave function of a free particle in quantum mechanics, the group velocity is twice the phase velocity, just right to represent the classical particle speed. The problem then is to determine the group velocity of a wave packet with the general form. Another equation, this in our case, blah blah blah. But what I have to say now applies to any kind of wave packet, regardless of its dispersion relation. The formula for omega as a function of k. Let us assume that Vk is narrowly peaked about some particular value k0. There is nothing illegal about a broad split in k, but such wave packets change shape rapidly since different components travel at different speeds. So the whole notion of a group with a well-defined velocity loses its meaning. Since the integrated is negligible except in the vicinity of k0, we may as well tailor expand the function omega k about that point and keep only the leading terms. This, well, omega. Oh, I just remember what is the name. It's accent. Omega 0 accent is the derivative of omega with respect to k at the point k0. Changing variables from k to s, blah blah blah, to center the integral at k0, we have another equation. At t equals 0, another equation, and at later times, yet another equation. Except from the shift from x to x minus 0 xn omega t, omega xn 0 t, the integral is the same as the one in capital C x0, thus another equation. Apart from the phase factor in the front, which won't affect the magnitude of capital C in any event, the wave packet evidently moves along at a speed group velocity equals to the omega per k evaluated at k equals k0, which is to be contrasted with the ordinary phase velocity. V phase velocity equals omega per k. In our case, omega equals this, so omega per k equals that, whereas another equation which is twice as great. This confirms that it is the group velocity of the wave packet, not the phase velocity of the stationary states, that matches the classical particle velocity. Okay, V classical equals V group equals to double the phase velocity. Okay, so we got to that problem. Okay, so let's rest for a bit. 5 minutes break, but probably not exactly 5 minutes. So yeah, I could. Uh, mm, uh, so guys, don't forget to hydrate and don't forget to hydrate and don't forget to stretch if you have sit in front of your computers for too long. Sleep well and treat this stream as a bedtime story if you want. Okay. Anyways, well, I have the other thing. Oh yeah, I heard that the Tekken is like discounted like it's a very big discount on Steam. Well, probably after this I will probably buy Tekken. Oh, oh, it's Mayday already. Yeah, so it's Saturday and it's Mayday already. So yeah, happy Mayday, guys. Happy Maydays. Yeah, it's it's kind of sad though, the Mayday itu apa, hari itu Mayday itu jatuhnya di hari Sabtu gitu, coba kalau di weekdays gitu jadinya ya ya kebuang, kayak agak sayang gitu, jadi nggak kerasa liburnya gitu. Yeah, so okay, this is the last capture, last sub capture probably, the delta function potential. Okay, let's go. We have encountered two different kinds of solutions to the time-independent Schrodinger equation. For the infinite square well and the harmonic oscillator, they are normalizable and labeled by a discrete index n. For the free particle, they are non-normalizable and labeled by a continuous variable k. The former represents physically realizable states in their own right, the latter do not. But in both cases, the general solution to the time-dependent Schrodinger equation is a linear combination of stationary states. For the first type, this combination takes a form of a sum of over n, whereas the second is an integral over k. What is the physical significance of this distinction? In classical mechanics, a one-dimensional time-independent potential can give rise to two rather than different kinds of motion. If Vx rises higher than the particle's total energy, E on either side, equal to 0.78, then the particle is stuck in the potential. Well, it rocks back and forth between the turning points, but it cannot escape, unless... Oh, what is this? Unless, of course, you provide it with a source of extra energy such as motor. But we are not talking about that. We call this a bound state. If, on the other hand, E exists Vx on one side or both, then the particle comes in from infinity, slows down or speeds up under the influence of the potential, and it returns to infinity. It can't get trapped in the potential unless there is some mechanism such as friction to dissipate energy, but again, we are not talking about that. Malam Pak Guru. Oh, hello Emerson, please welcome to my stream. Well, not exactly teacher. I'm just a book reader this tonight, because this is this is just only a book reading stream, not a teaching stream. So yeah, this is quantum mechanics. This is not an easy topic, so it's fine. It's totally fine if you don't understand anything about quantum mechanics. because yeah, me too. I too doesn't understand quantum mechanics. I'm just reading the book. Okay. Yeah, so I'm reading a bedtime story for you guys. Where, where am I? Where am I? Where am I again? Okay, we call this a from this. We call this a scattering state. Some potentials admit only bound states. For instance, the harmonic oscillator. Some allow only scattering states, a potential hill with no dips in it, for example. Some permit both kinds, depending on the energy of the particle. As you have probably guessed, the two kinds of solutions in the Schrödinger equation correspond precisely to bound and scattering states. The distinction is even clearer in the quantum domain because the phenomenon of tunneling, which we will come to shortly, allows the particle to leak through an infinite potential barrier. So the only thing that matters is the potential at infinity. Figure 2.70. Oh, this this figure. Okay. Another equation. In real life, most potential goes to zero at infinity, in which case the criterion simplifies even further. Okay, if the E is less than zero, it's the bound state. If it's greater than zero, it's a scattering state. Because the infinite square, well, and harmonic oscillator potentials go to infinity as x limit to 2 infinity. Yeah, the plus minus looks like a Chinese character 2, so I will spell it as 2 instead. They admit one states only because the free particle potential is 0 everywhere. It only allows scattering states. Oh yeah, the 2 in Chinese means it means ground. Okay, that's that's an unrelated intermezzo. Enough of the intermezzo. In this section and the following one, we shall explore potentials that give rise to both kinds of states. Oh yeah, so the Dirac delta function. Yeah, the Dirac delta function delta x is defined informally as follows. Oh, this is the function that is only it reaches infinity if the x is in 0, but in the other locations it is 0. With integral from positive infinity to negative infinity, delta x dx equals 1. Wait. Hey, wait. Wait, I just found something, man. You can pronounce the plus as sure. Sure to e. Well, the plus looks like sh and the minus looks like e in Chinese. Well, so in the okay, let's continue. It is an infinitely high, infinitesimally narrow spike at the origin, whose area is 1, figure 2.8. Technically, it's not a function at all, since it is not finite at x equals 0. Mathematicians call it a generalized function or distribution. Nevertheless, it is an extremely useful construct in theoretical physics. For example, in electrodynamics, the charge density of a point charge is a delta function. Notice that delta x minus a will be a spike of area 1 at the point A. If you multiply delta x minus a by an ordinary function, fx is the same as multiplying it by fa. Okay, fx delta x minus a equals fa delta x minus a, because the product is 0 anyway except at the point A. In particular, this. The equations, that's the most important property of the delta function. Under the integral sign, it serves to pick out the value of fx at the point A. Of course, the integral need not go from minus infinity to positive infinity. All that matters is that the domain of integration includes the point A, so a minus epsilon to a plus epsilon will do for any epsilon greater than 0. Okay. Okay. Okay, random fact. The delta direct function is not only a quantum mechanics thing. Apparently, it's also the... If you study signal processing, the Dirac, the delta Dirac function also exists. And not only quantum mechanics and signal processing, but also in control theory, I guess, and to some extent system dynamics and so on. So it's not a quantum mechanics thing. Okay, then let's continue. Let's consider the potential of the form the equation where alpha is some constant. This is an artificial potential, so was the infinite square well, but it's beautifully simple and in some respects closer to reality than any of the potentials we have considered so far. Schrödinger equation reads this. This potential yields both bound states and scattering states. We will look first at the bound states. In the region x less than 0, Vx equals 0. So equation where another equation E is negative by assumption. So K what is this? It's kappa. Yeah, kappa is real and positive. The general solution to equation 2.98 is another equation. But the first term blows up as x limit to negative infinity, so we must choose a equals to 0. And so the another equation in the region x greater than 0, Vx is again 0, and the general solution is of the form f exponent blah 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 blah. This time it's the second term that blows up as blah blah blah. As x approach into positive infinity. So another equation, it remains only to stitch these two functions together using the appropriate boundary conditions as x equals 0. I quoted earlier the standard boundary conditions for psi. 1. C is always continuous, and 2. The differential of c to x in the respect of x is continuous except at points where the potential is infinite. In this case, the first boundary condition tells us that f equals b. So, another equation, be kappa x if x is less or equals to 0, and be to the power of minus kappa x if x is greater or equals to 0. Cx is plotted in figure 2.9. Oh, so this is the plot. This is the graphic. The second boundary condition tells us nothing. This is like the infinite square well, the exceptional case where v is infinite at the joint. And it's clear from the graph that this function has a kink kink at x equals 0. Moreover, up to this point, the delta function has not come into the story at all. Evidently, the delta function must determine that the discontinuity in the derivative of c at x equals 0. I will show you now how this works, and as a byproduct, we will see why the derivative of c to the respect of x is ordinarily continuous. The idea is to integrate the Schrödinger equation from minus epsilon to plus epsilon, and then take the limit as epsilon approaches 0. Okay, another equation, the first integral is nothing but dψ per dx evaluated at the two endpoints. The last integral is 0 in the limit epsilon approaches 0, since it's the area of the sliver with vanishing width infinite height. Thus, another equation. Ordinarily, the limit on the right is again 0, and hence dψ per dx is continuous. But when the Vx is infinite at a boundary, that argument fails. In particular, if Vx equals minus alpha delta x, equation 2.95 yields another equation. For the case at hand, another equation, and hence equation, and the out energy another equation. So this page is basically full of equations. Finally we normalize psi c equation. So another equation. Oh, this is a readable equation. B equals to square root of kappa equals to square root per m alpha per Planck constant. Evidently, the delta function, well, regardless of its strength alpha, has exactly one bound state. This equation. What about scattering states with E greater than 0? For x less than 0, the Schrödinger equation reads this, where k is square root of 2me per Planck constant is real and positive. The general solution is this. Oh, yeah, it's called the general solution. And this time we cannot rule out a return since neither of them blows up. Similarly for x greater than 0, another equation, the continuity of cx and x equals 0 requires that f plus g equals to a plus b. The derivatives are long as equation, and hence delta dc per dx equals to I blah 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 to ik dalam kurung f minus g minus a plus b. Meanwhile, c0 equals a plus b, so the second boundary condition says equation, or more compactly, another equation where beta equals to m alpha per Planck constant squared k. Having imposed the boundary conditions, we are left with two equations in four unknowns: a, b, f, g. 5 if you count k. Normalization won't help since this is not a normalizable state. Perhaps we'd better pause then and examine the physical significance of these various constants. Recall that exponent ikx imaginary the I is imaginary, the imaginary number gives rise when coupled with the right time time dependent fractional exponent blah 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 to a wave function propagating to the right, and exponent minus ikx leads to a wave propagating to the left. It follows that a in equation 2.113 is the amplitude of the wave coming in from the left, b is the amplitude of a wave returning to the left, f in equation 2.114 is the amplitude of a wave traveling off to the right, and g is the amplitude of a wave coming in from the right, figure 2.10. In a typical scattering experiment, particles are fired in from one direction, let's say from the left, in case the amplitude of the wave coming in from the right will be 0, or this figure g equals 0 from the scattering from the left. A is then the amplitude of the incident wave, B is the amplitude of the reflected wave, and F is the amplitude of the transmitted wave. Solving equations 2.115 and 2.117 for B and F, we find this set of equations. If you want to study scattering from the right, set A equals 0 and G is the incident amplitude, F is the reflected amplitude, and B is the transmitted amplitude. Now, the probability of finding the particle at a specified location is given by the magnitude of C, so the relative probability that an incident particle will be reflected P is another equation. R is called the reflection coefficient. If you have a beam of particles, it tells you the fraction of the incoming number that will bounce back. Meanwhile, the probability of transmission is given by the transmission coefficient. This, of course, the sum of these probabilities shall be 1, and it is r plus t is 1. Notice that the r plus t are functions of beta, and hence equations 2.112 and 2.170 of E is this. The higher the energy, the greater the probability of transmission, which seems reasonable. This is all fairly tidy, but there is a sticky matter of principle that we cannot altogether ignore. The scattering wave functions are not normalizable, so they don't actually represent possible particle states. But we know that the resolution to this problem is we must form normalizable linear combinations of the stationary states, just as we did for the free particle. Raw physical particles are represented by the resulting wave packets. Straightforward in principle, this is a messy business in practice. And at this point, it is best to turn the problem over to a computer. Yeah, computation time. Meanwhile, since it is impossible to create a normalizable free particle wave function without involving a range of energies, R and T should be interpreted as approximate reflection and transmission probabilities for particles in a narrow energy range about E. Incidentally, it might strike you as peculiar that we were able to analyze a quintessentially time-dependent problem. Particle comes in, scatters off a potential, and flies off to infinity using stationary states. After all, C in equations 2.113 and 2.114 is simply a complex, time-independent sinusoidal function extending with constant amplitude to infinity in both directions. And yet, by imposing appropriate boundary conditions on this function, we were able to determine the probability of a particle represented by a localized wave packet would bounce off or pass through the potential. The mathematical miracle behind this is, I suppose, the fact that by taking linear combinations of states spread over all space and with essentially trivial time dependence, we can construct wave functions that are concentrated about a moving point with quite elaborate behavior in time. See problem 2.40. Yeah. As long as we've got the relevant equations on table, let's look briefly at the case of a delta function barrier, figure 2.11. Formally, all we have to do is change the sign of alpha. This kills the bound state, of course. See problem 2.2. On the other hand, the reflection and transmission coefficients, which depend only on a alpha squared, are unchanged. Strange to say, the particle is just as likely to pass through the barrier as to cross over the well. Classically, of course, the particle could not make it over an infinitely high barrier regardless of its energy. In fact, the classical scattering problem is pretty dull. If energy greater than potential max, then T equals 1 and R equals to 0. The particle certainly makes it over. Conversely, if energy is less than maximal potential, then T equals 0 and R equals 1. It rides up the hill until it's run out of energy and then returns to the same way it came. The quantum scattering problem is much richer. The particle has some non-zero probability of passing through the potential even if energy is less than maximum potential. We call this phenomenon tunneling. It is the mechanism that makes possible much of modern electronics, not to mention spectacularism advance in microscopy. Conversely, even if energy is greater than maximum potential, there is a possibility that the particle will bounce back. Though I wouldn't advise driving off a cliff in the expectation that the quantum mechanics will save you. Driving off the cliff and hoping that the quantum mechanics will save you. Okay, so that's all for that's all for today. That's all for today's stream. I will only read until 2.5. The rest of the chapter 2 will be read on the next stream, probably. So that's all for tonight. And stay tuned for my next stream. It will be Sunday, but I'm not even sure. But stay tuned on Sunday because yeah, I don't plan to stream on Saturday. So thank you guys for watching this stream, and if you are asleep or almost asleep, have a good night. Have a nice stream and good night. Bye bye.